Hello, so today we are going to talk about algebraic data types in Kotlin. So what do I mean by that? So algebraic data type in a nutshell is basically a data type that is kind of a composite type. So it's a type formed by combining other types. So for example, you could have a user, it's usually a username and a password. For example, user credential, a username and a password. So user credential is a composite type of username and credentials, right? It combines both types together. Um, and why the term algebraic is you can think of it as coming from algebra. You have algebraic operations like sum and product, and that's where it comes from. Now, why sum and product? We will see that in a moment, but essentially that's what it is. So there are two usually common classes that we talk about when we talk about algebraic types, product types, and sum types. So sum is a combination where you have either one type or the other. So you can think of enums, for example, as a sum type, because in all of the enums variant, it can be either one of those, right? A product is usually a combination. In the earlier example, I spoke about user credentials where you have the username and the password. Those are a combination, right? You combine both and you get the final type, right? Um, Now let's take a look at some example to really make sure it's clear. So product types, let's see some examples. Some lightweight ones are usually pair and triple types in classes in Kotlin. So pair is just a combination of two types, right? For example, it can be a combination of integers. For example, here 10 and 20. Triple is a combination of three types. It can be string, int, boolean, so a combination of three. Data classes also are a type of product types, because you have name, for example, age, and email. Person is the combination of all three. Now, why is it called product? Because, for example, if we look at pair, okay, we have two integers. We can have as many integers multiplied by as many of the other types. So let's say, for example, if we had pair of two enums, and each of the enums had only two types possible, then the pair would have only four types possible, the product of the number of elements of each, right? So you can think of product types as basically a record that has some attributes. Those attributes constitute the product type, which is the data class that we define, right? And that's what I mentioned earlier. Here, just another example where you have a set of shapes. Let's say we have only two of them, circle and square, and we have a set of colors. Let's pick only red and blue, for example. So we have only these two sets, circle and square, and red and blue. Now, if we have a type that is a pair of the two, of the shape and color of S and C, then the product type that is the pair of both would have combinations of both, right? So we can have circle and blue, circle and red, or square and blue and square and red, right? Those are the only possible combinations, and that's why it's a product. We have four combinations, which are resulting basically from 2 multiplied by 2, from the number of elements in S multiplied by the number of elements in C. Okay, so the other types of algebraic, or the other variant of algebraic type, is sum types. And usually there are two examples. It can be enums. Enums are good examples of sum types, or sealed hierarchies. And by that I mean like sealed classes or sealed interfaces. So an enum, for example, here, an enum of all the days of the week is a sum type. Why is that? Because day is the sum of all the possible enum values, which 7 here, right? Okay. Or it can be a sealed class, like here we have shape and we have circle, rectangle, square. Each inherits from shape, and we have these three types. Now, why is it called a type? Because any value that has a type of shape can be either circle, rectangle, or square. So we have only three variants. So 1, 2, and 3. We sum them up together. Same thing for day. We only have 7 variants. That's why it's the sum of the values of each. Similarly, you can have an interface like network response, and it can be either a success, an error, and or a loading. It can be only one of those 3. Okay, so why is it called the sum type? Again, just to reiterate it a little bit more. Let's say we have a payment method. It can be cash, it can be just credit card or PayPal. Let's say we don't have cash. Now, these are data classes. Each of them has its own attributes, right? So let's say we have n possible values that credit card can take on, right? For some reason, that n values may be all the different combinations of credit card numbers and CVV. PayPal also all the combinations of email. Let's say it's m values. Then the type payment methods can only be n plus m values, right? So it's the result, the composite type is the combinations of the possible values of each of these data classes that inherit from it, right? And so that's why it's called sum type. Now, why do we even need algebraic data types? Why do we use them? What are the advantages? One of the first advantages, and especially it relates to sum type, is compiler enforced exhaustiveness. What I mean by that is the compiler already knows all the possible values a type can have, because, for example, payment methods, it knows that it can be either credit card or PayPal. It can't be anything else. And so if you add something else, let's say cash, then all the methods that use the type payment method, the compiler will prompt you to handle that new value, right? If we take another example with the network response that we saw earlier, let's say we have success, error, and loading first, right? And we have a function that uses pattern matching here with when on the 3 values, right? Let's say afterwards, maybe they are even in different code files. We add timeout, okay, with the duration. Now, this handle response will not compile until we handle in our pattern matching here, until we handle timeout. That's extremely useful, because if we hadn't had this and it was a runtime check, like if the response is success, do something, if the response is do errors, and maybe even it was like a status sort of thing with string, then you won't know that you didn't handle timeout until maybe you test later on or something. But here it won't even compile until you handle it, and that's very helpful with making sure you don't have bugs. Now, another thing we are going to talk about is how do you also use algebraic data types to reduce bugs, another types of bugs which can happen if you are able to present states that should be impossible. What do I mean by that? But I think before explaining that, I need to explain a little bit something called thinking of types as sets and the cardinality of sets. It's a little bit of a mouthful, but bear with me. I will explain first what I mean by thinking of types as sets and what I mean by cardinality here, and from there we will get to the concept of how do we use that to reduce bugs when we are implementing or coding our functionalities. So let's just take a look at primitive types first. So booleans you can either have true or false. So that's very simple. You have only 2 possible values, okay? And so a cardinality basically is the possible values of a type, okay? With boolean, pretty simple. You either have true or false, okay? If you have a byte, you have 256 possible values, 2 to the power of 8 possible values. So that's the cardinality of the type. So we think of the type as a set, and we think about what's the cardinality of that set, which means basically what are the number of elements in that set. Boolean, we have only 2. If we take Boolean, optional Boolean, now we have 3 because we have true, false, or nil, right? So now we have 3. If we have an integer, we have 2 to the power of 32. If we have long, 2 to the power of 64. String is infinite, right? You could have as many characters as you want, infinitely. So it's infinity. Now int, optional int, is the number of ints plus the nil value as well. So that's what cardinality is. It's just the number of values that, if we think of a type as a set, how many values are in that set. Now, thinking back about the 2 algebraic types that we can have, which are product types and sum types, let's think about how do we calculate cardinalities of a product type and of a sum type, right? So for a product type, it's pretty straightforward. Product is a combination. So if you have, let's say, the simplest one, which is a pair of 2 booleans, we know each boolean has a cardinality of 2, then it's just the multiplication, 4. Why is that? Because think about it. If you have 2 booleans, then it can be, each boolean can be true or false, okay? And so you could have true, 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 false, or false, true, or false, false, which is just 4 combinations. Now, if it's a pair of Boolean strings, you can have only 2 Booleans, but you can have an infinite number of strings. So it's, you can think of it as 2 multiplied by infinity. So it's also infinity. For triple of 3 Booleans, then you have 2 for each, and it's just 8. And if you can even draw it down and try it out, you will see that it's you only have 8 possibilities for this type, for the type triple of Boolean, Boolean, Boolean. Now, if we have characters, each character, assuming it's a Unicode character, is going to be 1043,859. Then you just multiply all 3. You get how many possible values for that type. Now you can see the more we have in the more types we have in a product types, the more potentially the number of possible values will increase, right? Now, if we have a type like string, it will increase infinitely, right? Another example, let's say we have a data class, not just an existing pair or triple types. Let's say we have our own device status that has a status code and whether it's active or not. So active is Boolean, so only 2 possible values. Byte, we said earlier, it's 2 to the power of 8. So for byte, we have from -128 to 127. So the possible values of device status, which is its cardinality, is 256 multiplied by 2, so 512, okay? So basically, each byte can be paired with either true or false. That's the idea here. Now, similarly for sum type, sometimes it's the sum, right? Because, for example, if we have an either type, either it means we either have one value or the other. So we could have either Boolean or string. Boolean, we only possible 2. String, infinity. It's a plus because we can only have one or the other. Similarly for an enum, you can only have, for example, for a dice face, you can have 1, 2, up to 6. Okay, so the cardinality is each of them 1, and we add that together, we get 6. We saw this example before. Payment method, you can have cash, credit card, or bank transfer, right? So for cash, only 1 possible value. Credit card, since we don't have any parameters for it, if we had, then it would be different, but in this case we don't, so it's only 1 possible value. Bank transfer, because it has amount double can be infinite. It has infinite number of possible values, it's infinite values. But the sealed class itself, as a combination of all those, it's 1 plus 1 plus the infinity from bank transfer, right? That's the final cardinality, okay? Now, why does this even matter, all this talk about cardinality of a set? Well, the thing is, the more you have a smaller cardinality, the easier it is to manage, because remember, why do bugs happen? Bugs happen because we end up in a state that we didn't account for, or we didn't handle properly, or that state shouldn't even exist. That's what bugs come from. If we have a smaller cardinality, we can anticipate all the cases and handle them, right? That's the idea. And even in testing, the smaller cardinality, the easier it is to test, because we can't test every variant if we have infinity, right? So that's the core idea behind this, is to give you a way to think about how to represent your type in a way to reduce the cardinality so it's easier to handle. So let's take a look at a real world example here on how can we use the concept we just saw to model some data. So going back to the payment method example, if we want to represent a payment method, we can just have a type alias for string. We can just use string, right? But again, string cardinality is infinity. And so we have an infinite possibilities of invalid states. Why? Because let's say this string we accept only cash, credit card, and PayPal, and those get represented as strings. Then we need to do some runtime validation to make sure it's equal to one of the three. But what if someone writes cash with a C, for example, right? So you can see we have to either do runtime validation, and there is an infinite number of invalid states. So we can't check. And if we add another payment type, we also have to add that in our runtime validation. And the problem with runtime validation, again, is that the compiler can't tell us. So if we forget, the bug is hidden there, right? You may think about a better approach to do this, which is, okay, the cardinality here is infinity. Can we improve that? And you may say, okay, let me just have payment flags where each type is Boolean says whether it's credit card, the Boolean would be true. If it's PayPal, PayPal would be true, etc. Right? Now, again, this one is better, but still problematic because remember, we have a product type, and the product type is the multiplication of the possible values of each. So here, credit card Boolean 2, PayPal 2, and 2. So we have 8 possible values. Okay? Now, actually, if you think about it, a payment method can be only one of the 3 types. It can be 2 at once. And so the valid states are actually only 3 valid states, right? Where one of the flag is true. So only true, false, false, or false, true, false, or false, false, true. That's the only 3 valid states. We have 5 other invalid states. I listed them out here. And so we need to check against these invalid states. We need to check that only one flag is valid. Let's say if we add more payment types, this invalid or valid state check is going to be cumbersome, right? So this one better than the previous string method, but still not ideal. And I invite you to, even whenever you have a data class where you add 2 booleans or even 1 boolean, to think about, okay, can I represent this in a better way? And the better way is actually using a sealed class, a sum type, where now you say it's either a credit card, a PayPal, or a bank transfer. So you encode the possibilities here, and you cannot have any more invalid state. So here, what's the cardinality? Well, it can be either credit card, PayPal, or bank transfer. So 3 actually. Only 3. The cardinality is only 3. We can't represent any invalid state. You can't represent here a payment type that is both a credit card and a PayPal. You can't even. And so you have first the safety of having only one payment method. You can only represent you represent something, a payment method, as one of these variants. And then the other thing, if you add a 4th one here, let's say maybe cash, then if you add cash, for example, then you are the compiler will not compile until you handle that in all the pattern matching expressions, in all the usages where you distinguish all the variants of payment method. Okay, so that's why it's useful. And you can see this here, because we have a smaller cardinality, we can manage it. Another example that is a little bit different that I want to talk about is another way to eliminate impossible states. So let's say we have, and this is often you have this on Android, where you have, or any UI framework or any UI application, where you have your model that has the loading state, either a loading state or you have the data. So either you are fetching, you are in a loading state at that moment, and then when you have the data, you have the data value not nil, right? This is a product type, okay? We can have either two booleans. Is loading can have only two possible values, true or false. Data, depending on the data type, it can have as many as the cardinality of data. But the problem here is we have two possible invalid state that we can still do. We can define a model that has is loading at false, but the data is null, right? If we had an error, then at that moment error should be true, maybe. But here, since we don't have error, we should have either one of the two. Or maybe you have is loading true and data, you have some data. That will be a bug in the UI, because maybe you will see a loading spinner at the same time you'll see a list of results. So that's a bug. So how do we fix this? And the answer here is to move to a sum type, where you have only two possibilities. Here you can have either a loading or a success. So one or the other. You can't have both at the same time. And to do that, we can define a result state. For loading, we have no results, so we parameterize it with nothing. For success, we have some data, so that the data is the parameter here. And for our model, we just, this needs to be result state. And then and then our definition, if we are in a loading state, then we just pass again result state dot loading. And if we are in a success case where we have the data, we just pass result state dot success and pass the data. And you can think of here as we have some values, right? And now you can see we can't represent the case. You can't even in the types define a case where you have no loading and no data. You can't. You have to have one of the other. And you can't define a case where it's not loading and it's not success and you have no data, like loading false and no data. You can't represent this in the type even. So that's the strength of this approach. And the cardinality here is we have, for each of these we have only two possibilities, but the success case depends on the data type for data, but it's less than if it was a product type where we'd multiply the variance, the number of possible values. So that's pretty much it what I wanted to cover today about algebraic data types, and stay tuned for more about Kotlin types in the future. Thanks for watching and see you on the next one. Bye.